Okay, so yeah, I was saying midterm season is coming. So for the first years, right? This is where you, you know, students start to experience, start to get stressed about the midterms and things like that. So yeah, and I guess my advice will be the same for almost all courses that everyone is taking, is that yeah, if you start studying early, it will not be as stressful as studying last minute, especially for things like physics and math courses. It is always like good to study early from the beginning and spread out rather than one shot study overnight without sleeping, that kind of thing, because physics and math is about practice, right? So before we begin, right, let me mention this a little bit before I forget. Yeah, by the way, thanks everyone for coming to my talk on Friday. That was quite fun. This Friday, we will have another talk. It is the undergraduate math seminar organized by the math department, and Dr. Gloria Teng will deliver a talk about machine learning. And I have sent an announcement, and you can get the links to there, and you can attend the talk as well if you are interested. So machine learning is a field that is becoming very, very important in many different areas. So even for those of you who are interested in astrophysics, right, one of the things that surprises many students is that astrophysics and cosmology actually involves a lot of statistics. So it is one of the things that I didn't learn properly last time. So but today is being used a lot. So if you just check the archive, right, where all the recent papers are submitted, and you can see already, machine learning is being applied to solve a lot of many different problems in astrophysics, like black hole mergers, machine learning and things like that. And this is just within the last week, the papers within the last week. So every once in a while, there are some new papers coming up involving machine learning. So if you're interested, you can go and take a look at the talk. Besides that, yeah, let me remind everyone again, we have quiz 1. So it will be on Wednesday to Thursday. So the quiz 1 page will unlock on this time, and then we have 24 hours to do it, right? And then midterm exam will be coming soon. So the topics covered will be chapter 1 to 5 for the midterm exam. Our midterm exam will be on given the situation, right, it's most likely is going to be online, and we will do it through the Moodle. So it will be the same format that we will do on the quiz. That means there is a deadline. Although the midterm is not one day, midterm will take place in 2 hours, and within the 2 hours you solve the exam. You will have extra half an hour to scan and prepare your PDF file for submission, and everything will be submitted through Moodle. Okay. Yeah, so the math students who have done the semester, April semester last round, is probably familiar with this situation. So the physics students who are new, well, it will be the similar to the what we will be doing with quizzes with this course, and probably your other courses as well. Wei Zheng said scan solution. Yes, correct. So just need to scan the solution. Yeah. So okay, the question style, yeah, more or less the same. And basically they are physics question. The style is the same. That means got question, and then for midterm maybe at most there are part A, B, C, right? So so midterms, for each question there are parts A, B, C, and then you answer them. But besides that, yeah, they are all the questions we have been doing so far in the tutorial. Scanning, yeah, so no problem. I guess everyone by now should have your preferred or favorite scanning app, or maybe you have a scanner at home, I don't know, or the scanning app. Then just use that, and then make sure it's in PDF file. Besides that, there's no other important things to say. Oh, you want me to recommend an app? I don't know. So seems like a lot of people use cam scanner. Yeah, a lot of people use cam scanner. what I did for uploading our notes, right, is I have been using the Dropbox scanner. So, but then you need a Dropbox account. So if you have Dropbox, right, I quite like the Dropbox scanner. PDF Expert, is that an app? Maybe, I don't know. Then yeah, that's Cam Scanner is the one that I know that many people use lah. Yeah, so PDF Expert. Yeah, so if you are free, right, in the meantime, you can browse around for different apps, and because you'll be using this a lot throughout this semester, right? So okay, so besides that, let's get started. We are starting a new chapter now, so let us talk about rotational motion. Okay, so let me introduce to you the motivation of why we want to study. And I guess everyone here already kind of knows the motivation, because when we were discussing chapters 1 to 4, right, a lot of you have already been asking, why have we been ignoring the size of the object? Do we care about the configuration of the box and things like that? And every time I sort of push the answer to chapter 5, saying that for chapters 1 to 4, we just treat everything as point particles. Even if they are not point particles, we just look at the center of mass, and then we see how the center of mass moves, right? So that is what we have been doing for chapters 1 to 4. But right now, we will have to start to consider the sizes of the object. Okay, so yeah, so last time, right, we were just, in the previous part, we just talked about the center of mass, and then if we see if the object is having a mass m and then it's moving at some velocity v, right, even though it has the size, right, length and width, we just treat them as some particle, right, where the center of mass having a mass m, and then we just see how that particle moves. Okay, and what this means is that we have been talking about this motion, and this motion specifically is called translational motion. Translation motion, yeah, it just means this, because what we're about to do now is to study the second type of motion, which is the rotational motion. So rotational motion, therefore we just this is a new type of motion again, so we start again with the basics. That means we start from kinematics, right? So rotational motion, what we're going to do is to study how things rotating stuff, right, like the fan and the bicycle wheels and things like that. Let me remember to pull this up for the OBS. So yeah, so we are talking about these kind of things now, and of course there's many things that involves rotation and turning, right? So even kinematics itself is a complicated issue, although luckily for us we do not need to worry much about it, but I will mention a bit. Is that there is a branch of physics and math which is called IK, inverse kinematics, and it's being used in designing of robot arms and things like that, because if you want to design a robot hand, right, like for example those robots that use in the factory, so they have to rotate, and then the positions, because of the rotation, the different points will go to different positions. So if you want to program this type of motion, the math becomes very complicated, right? So this picture here, I take this example, is more interesting in the world of game design. So even in game design, I talked about projectile motion last time, but rotational motion also is quite important, because if you play games nowadays, right, your video game character, for example, if your video game character is walking up the steps, right, you need to animate the motion of walking the steps correctly, and that means to make it look realistic, your video game character, the legs, right, the legs must be placed at the correct position of the steps. And if you play any game, you might notice that it's quite interesting how your character can put the leg at the correct place automatically, no matter how you control the character. And this is because the inverse kinematics equation sort of calculated to rotate the joints to put your feet at the correct place. So for math students, right, you might encounter this even more when you learn more about algebraic geometry. That is a higher level course in the math program. So the methods of algebraic geometry will be used to solve this, as well as rotational kinematics. So let's get so that is sort of the taste of even just kinematics itself. We haven't even talked about forces and momentum. Just kinematic is already a big field and big area of research and applications and things that many people try hard to solve. Okay, so yeah. By the way, I wonder if anyone recognized the game that I put in the picture. Yeah. So let me know if you can recognize what game is that. You can tell me. Otherwise, let us get started with this. So we are going to talk about rotational motion. And in particular, we want to talk about the rotation of rigid bodies. So let me define what is a rigid body. Okay, so we will be studying mostly rigid body. And from the name also, we can already tell a rigid body is something solid, right? If it's something solid, then it's just one piece. And if it's just one piece, so if you rotate, everything rotate together at the same amount. So rigid body is, these are objects of finite size. Okay, and then it can undergo two motions. So this is one word. My handwriting sort of put it too far away. So of course, rigid body, we have been, so like boxes like this, right? It is one example of a rigid body, and we have been treating the translational motion in the in chapters 1 to 4, right? Linear momentum, forces, those are strict things. And then secondly, now we will study the second way it can behave, which is the rotational motion. Okay, so rotational motion, now it is rigid, right? So that means firstly, this rotational motion is, we will consider it rotating about some axis. Of course, when we talk about rotate, we need an axis of rotation. So there's going to be some axis. So the axis of rotation is important. And what do we mean by rigid? So rigid means all points of the object, they rotate together at the same angular velocity. Okay, so all points on the body, on this rigid body, rotate in circular motion. Of course, it has to be circular motion, right? If it's elliptical motion, that means the point will like bend away from the body or things like that. So circular motion around the axis with the, so this is important, the same angular velocity. So we will see later that angular velocity must be the same, therefore the linear velocity of each point will be different. Okay, so this is the idea of the rigid body. So when we are talking about those like inverse kinematic things, right, the factory arm, right, so they're just like robot hands, right? So you need to program how they rotate. So these are rigid body, right? So your arm is one piece. So if you rotate about the axis, the how many rounds per second, they all have the same angular velocity. You cannot have the different angular velocity, otherwise the different piece will separate away. That is what it means by a rigid body. Okay, so everyone, Dark Souls. Yeah, everyone can recognize Dark Souls. So this is the PDF software, right? Oh, your physics lab is doing this. Okay, I see. Yeah, this game is Dark Souls. So the picture is from Dark Souls 1. And yes, it's a paid game and you must pay to suffer, unless there's a discount. Unless there's a Steam sale or something. Okay, so yeah, so now we want to describe how an object rotates. So here we have, so let's talk about how to describe rotation. Rotation is, of course, is all about angles, so we need to use angles. Now in this chapter, we will be using mostly radians because it is more convenient. why more convenient is that oftentimes we will want to regularly convert the angles into arc lengths or displacements. So we can use the S equals to R theta formula. So this is what we will do. So we will write how to describe rotation. Okay, so for describing rotation, firstly we can talk about the angular displacement. So basically we are learning the same things as we did last time, like displacement, velocity, acceleration, but we now have angular. So angular displacement, angular velocity, angular acceleration. So let's say I have an object, right? I have an object like this. Okay, so I have an object like this. And then so I have an object like this, right? And then let's say I still have my x-axis over here, and this is my origin. Okay, and then for if it's a rigid body, right, every point rotates around the same angular velocity, the same rate. So we just take one representative point and see how it goes, right? So we mark the location of one representative point. So let's say the initial angle here of this point from the x-axis is theta 1, and then after it rotates at some later time, okay, so after it rotates at some later time, maybe it will go until, I don't know, let's say it's go until here, right? So my point has went until here, so the new angle is theta 2. So from here we see that my angular displacement is just the change in the angle. So it's just like our regular linear displacement. So it's the final position minus initial position. Just that today now is just we're talking about angle. So everything is the same. Okay, so pretty much the same thing that we have here. Okay, so yeah, so that is the idea of the angular displacement. So as I was saying, right, we are going to use radians. So let me remind everyone how to convert radians into angles. So 1 radian, right, is just 360 over 2 pi degrees. Okay, so yeah, so if you want to convert the radian, you can just times 180 over pi. That will convert degrees into radians, and then vice versa, we just flip it around. So everyone should be able to are familiar with the concept of radians, right? Or at least, you know, everyone probably knows from since high school, but now it's important to be familiar to how to convert from one to another quickly. And the reason why we want to do radians is because most of the time we want to calculate the, let's say from here to here, what is the distance covered, right? So the distance covered for a radius r is that the arc length is s is equals to r theta, and this is only true if you use the units in radians. Okay, so now, so this is the angular displacement. Important thing about this, right, that, and also a possible source of confusion is that we need to discuss about the sign convention. Okay, because eventually we want to calculate angular velocity. The tricky part about rotational motion is that the angle velocity must have direction, right? It has forward, backwards. You will also talk about angular acceleration, so it had acceleration and decelerate. So there's something positive and something negative. So what do we mean when we say it's positive or negative? For this, I guess for our purposes, what it is just important to just decide on the convention and then stick to it consistently. Then if you stick to it throughout the rest of the question, you will be getting the correct answer, right? So yeah, so let's talk about sign conventions for rotation. Okay, so sometimes, right, people might say that, okay, rotating anti-clockwise is positive angular displacement, and then therefore clockwise or clockwise will be negative. This is one choice that you can make. Second choice is just the vice versa, right? So anti-clockwise corresponds to negative, and then clockwise will be positive. Okay, so there's basically I'm just listing this, but it doesn't really mean anything. I'm just telling you that you can decide your own convention for yourself, but must be consistent, right? You don't do halfway and then suddenly you change the direction, and then that's how we get wrong. It sounds very trivial now, right? It sounds very trivial now, but so it sounds like something very simple. So why am I spending so much time talking about it, right? The reason is because when we start to talk about the second part of rotational motion, chapter 6, rolling motion, where we mix up rotation and translational motion at the same time, so the direction also start to get mixed up. So it is important to keep track of your positive and negative. So that is where, you know, many students will make mistake in the calculation and things like that. Okay, but as long as we just stick with it, right, just follow the consistently and don't forget the directions, everything should be fine. Okay, so yeah, so that is the sign convention. Now that we have defined angular displacement, we can quickly talk about all the other quantities, the similar quantities that we learned in chapter 1. For example, the average angular velocity. Right, last time we talked about average velocity. Now is the angular velocity. Right, so we call this omega. We have been using this symbol already before, right? It's just the change in rotation over the time taken, right? Or sometimes you say that final angle minus initial angle, this time minus the earlier time, and then the instantaneous angular velocity, right? It's just the omega, and we just need to, same as linear case, we just take the limit where the delta t goes to 0, right? So taking this limit delta t goes to 0, it just means that this is the derivative of theta with respect to time. So it just sees how the angles rotate. Okay, so yeah, so the units, we have talked about this before, I think, right? But it is pretty straightforward. It is just radians per second. Okay, so this is the unit for angular velocity. Another thing that is potentially a bit confusing is how do we describe the vector for angular velocity, because velocity by right should be some kind of vector, right? So vector for angular velocity, okay, to describe a angular velocity vector, we will use the right hand rule. Okay, so let's say I have some rotating object over here. Okay, so I have a rotating disk. Okay, and this is my axis of rotation. So axis of rotation, so maybe it's going this way, right? So right hand rule is this, and I know like different schools will teach different rules for this right hand rule, but the way I use the right hand rule is this, right? So you take your right hand, okay, and to write down a vector for angular velocity, why am I talking about it? So for vector, right, we need to have magnitude and direction. Okay, so the magnitude is this one, no problem, right? So we can do it by calculating this. But what is the direction? So to determine the direction is the right hand rule. So we take our right hand, right? So if I put my right hand, and then basically I will use my fingers my 4 fingers to follow the rotation, and once it's following the rotation, my thumb is pointing along the axis of rotation. Can you see? Right, so it's pointing along the axis of rotation. Therefore, the direction of my thumb will be the direction of my vector. So omega is pointing this way. Okay, so it's having a magnitude and then some direction in some unit vector, right? So this unit vector is pointing up. Okay, so this is how we describe the vector. So so for the omega, right, again direction, we determine using the right hand rule. And then magnitude is omega is the theta dt. Okay, so that is basically what we get for the right hand rule, right? So yeah, so the next thing is the angular acceleration. So let's talk about angular acceleration. And this one, everything is just like before, so I'll go through very quickly. The average angular acceleration, we call this symbol for angular acceleration. So the average angular acceleration is just the change in angular velocity over the time period it changes. So final omega minus initial omega time, this time minus the earlier time, then the instantaneous acceleration is just alpha itself. Just take the limit when delta t goes to 0, d omega dt. So this is the derivative of omega with respect to t, and therefore this is the second derivative of the angular position with respect to time. Okay, and angular acceleration, because it is an acceleration, it also needs a vector. So vector for angular acceleration, okay, so again, let's say I have some rotating thing over here. Okay, and then this is my axis. So if I, just now we were using the right hand rule, right? We have determined the omega to be this vector, and the direction of the angular acceleration is the simple way to remember is that the deceleration will oppose velocity, right? Acceleration will be in the same direction of velocity. So we point this direction if omega is increasing in speed, and pointing down if omega is decreasing, if omega decreases in speed. Okay, so this is the angular acceleration. Does anyone follow so far? It looks like Monster Hunter. Yeah, people compare Dark Souls to Monster Hunter a lot of the time, but Monster Hunter is a bit easier, probably. I don't know. Right. Yeah. So this is the angular acceleration, right? So everyone have no problem with this, right? Now that we have learned the basic concept of equation, then what naturally follows is the kinematic equation, right? That is also quite important. So we will have angular kinematic equations for constant alpha. Right, we did this last time for constant linear acceleration. We derived a bunch of equations. So we are doing the same for constant angular acceleration now, but everything is the same, right? So starting with the usual thing. So if alpha is a constant, right, that means the omega dt, which is the definition of alpha, this number is constant. So if this number is constant, then we can just integrate, right, both sides of the equation. So if I start from some initial velocity at time 0, and then at some later time I will get some later velocity, so I got this as my result, so alpha t. So we got this kinematic, our first kinematic equation over here, right? And then we also remember that omega is just the derivative of angular position, right? So we can integrate both sides. So I can integrate theta, and then on the right hand side I integrate omega plus alpha t dt. So from 0 and initial angle to some later time at some later position, so I got this minus this is equals to omega t plus half alpha t squared, right? So I got the basic kinematic equation, and I guess you can derive the rest if you want. Everything is just identical, just the change v to omega, change a to alpha, and things like that, right? So pretty much the same things. Okay, is there a question? Acceleration is upwards parallel to axis. Yes, yeah, correct. In this picture, you mean? question. Yeah, so we'll be treating parallel to axis. Basically alpha is the rate of change of this vector. So if it's parallel, right, it will just make the length grow larger, and it's pointing down, it will just make this length grow shorter until 0 and then point downwards. Okay, we will not consider where alpha has different direction than omega. So alpha has different direction omega, right? That means the axis of rotation will change orientation. So that one will be more complicated. So we will not deal with this at least in this course. Okay. Okay. So let's do some questions. Okay. The example. So this is the picture to describe. I don't even dare to draw this in my notes. So just use this picture. So a simple application is this, right? You have a Blu-ray disc that is finished playing and is slowing to a stop. So the disk initial angular velocity at time 0 is this many seconds. So let me write the information down. So the initial omega is 27.5 radians per second, and then the angular acceleration is -10. So just alpha is -10 radians per second square, and then a line PQ is just to represent the angles, and it at t0 it is along the x-axis. So that means at time 0 the angle is 0. So theta 0 is 0. And the first question is, what is this angular velocity at time 3? Okay, so just pretty straightforward. We just need to use the kinematic equation to solve. Okay, so we just use this equation, omega 0 plus alpha t, and just use the given information. The alpha is -10, and the t that we want is 0.3, right? So if we calculate this, we get 24.5 radians per second. And then the second question is asking us, at what angle does this make with the positive axis at t? So that means we want the angle, right? So we want theta. What's theta at t 0.3? So we just use this formula. So plus omega 0 t plus half alpha t square. So initial angle is 0. This is 27.5. 0.3. This is half. This is -10. This is 0.3 square. This is 7.80 radians. Okay. So I'm going fast because I think this is pretty straightforward, right? Everyone will just put in the formula, so it shouldn't be a big deal. Otherwise, otherwise tell me to slow down. Okay. So I think everyone is okay. Now is the more like less boring part. Okay. So previously everything is the same, right? Everything is just repeating this, but now is what is more things start to happen if we relate linear motion to angular motion. Okay. Okay. Yeah, so let's see how's everyone doing. Sounds complicated. Can't even do transformation in 3D. What you mean this example, is it? This example here. Oh, the alpha direction. Yeah. Okay. Yeah. Then don't worry. We will not deal with vectors a lot in, at least for now lah. We just so don't worry about the vector part. We will only in the higher level courses, maybe we will use it more often. For at least for now, right, to start with, we just need to remember the most basic thing, right? Angular rotation omega. Then we just need to see whether it speed up or slow down. right? Whether it's speed up or slow down, this only this thing. So just thinking in this language, that is just like our just common sense, right? If something is speeding up, so omega go faster, right? If something is slowing down, omega will decrease. So that is all. That is all we need to deal with. So we don't need to deal with the vectors here. So everything should be fine. But yeah, so the harder part will come in, not related to vector, I would say. It's probably about the rolling motion. So this is in chapter 6. Yeah. Okay, so let me draw this circle nicely. Right, looks good. And then this is the center of the circle where the axis of rotation is. So let's say, right, I have some object that is having this center axis of rotation, so it will rotate like this. Okay, and this is a rigid body. Okay, so this is a rigid body. By definition, we mean to say that every point on this body, right, it will rotate together. So let's say I have one point that is having position 1, this distance from the center, right? So so as it rotates, by the definition of rigid body, every point rotates in circular motion around the axis. So this point is going in the circular motion of this radius, and for circular motion it will have this instantaneous tangential speed, and it should be perpendicular to the circle, right, the direction. Okay, so we have learned how to calculate this before, right? But every point has the same angular velocity. So if you look at another point, right, so let's say I have another point over here. So a second point, let's choose this second one, V2. Okay, so this point, because this is a rigid body, so this one will also rotate in a circular motion around the center. Okay, but the radius of the circular motion is different. So this is R2, and then the speed here will be V2. Okay, so I don't know whether you already agree with me or not, but the speed V2 should not be the same as V1. Understandable, right? They cannot be the same, right? If you want omega to be the same, the speeds must be different. Okay, the reason is because we are talking about rigid body. So rigid body is every point is going in circular motion, but it's also having the same angular velocity. The same angular velocity. Okay, so if this rigid body is rotating omega, then everybody is going at omega. Okay, so how do we relate? We have learned, so let me review, right? We might have learned this before previously already, but let us look at this piece. So let us look at one object, right? Okay, so this object is having a distance r from the axis. Okay, and as it goes, as the body rotates, right, this point will go in circular motion. So let's say let's take one short time period, right? So it will, during this rotation, it will rotate by an angle of delta theta, right? And then the arc length it travel will be delta s. Okay, so the tangential speed is roughly along having this velocity vector. Okay, so the tangential speed, right, okay, is defined to be v tangential is equals to the arc length, the change in the arc length over time. Okay, so this is ds dt, right? But we also learned the formula that for a radius r, s is equals to r theta. So that means what we're doing is we are differentiating r theta over here. Okay, and because this is a rigid body, every point is going in a circular motion, so it is a fixed distance from the axis of rotation. So every point of a rotating object will have the constant distance. So I'm just trying to convince you that r is a constant, so I can take it out of the differentiation. Okay, and this part is, you notice, is the omega. So this is, again, I have re-derived the formula that v tangential is the radius times the omega. Okay, So that is the relation that we will be using a lot. This is why I'm deriving this again in a slightly different setting. Okay. Now, for the rigid body, everyone must have the same omega. So if the points have different radius, right, and this must be the same, then this V tangential must be different as well, right? If omega is constant, so if different R will give you different tangential speed. Okay, so this is why the different points along the body will have different accelerations, different velocities. Okay, and by the same token, right, we can also calculate the tangential acceleration. Okay, so the tangential acceleration is A tangential. So A tangential is just the rate of change of the V tangential. Okay, and we have seen that V tangential is just R omega, and R is a constant, so it's d omega dt. And this is what we recognize as the instantaneous angular acceleration. So we have derived the tangential acceleration to be R alpha. Okay, so this part we have filled in the gap that we actually secretly skipped over in chapter 1. Chapter 1, I was focusing a lot on the radial acceleration, right? V squared over R. So there's the tangential component as well, and I just say, okay, depends on the question magnitude, but now we can sort of have some formula related to it. Okay, so let me write this out for future reference. We have filled in a gap in chapter 1, the part about circular motion. Right, so remember when we're talking about circular motion, we talk about the radial acceleration. So this is the v squared over r, and I have implied that this is the tangential velocity. So this is because this is a tangential velocity, I can substitute v equals to r omega inside. So we got r omega squared, right? And then now we have learned the tangential acceleration is just the r times the angular acceleration. So so in chapter 1 we sort of ignore this part because we haven't talked about this yet, but right now if we somehow know the angular acceleration of a rigid body, we can calculate the tangential acceleration of the points around it. Okay, so yeah, so now we have learned. So let me remind you what is this situation. Okay, so acceleration, right, has for an object going in this particular circular motion, it has this component, which is the radial component and the tangential component, and the total acceleration vector is the vector sum of these two vectors. Okay, so now we can get the magnitude of both. The direction is already fixed, right? Radial direction and tangential direction. So we should be able to calculate almost any circular motion situation now. Okay. Any question? Okay, no question. Okay. 5.3 kinetic. So so if everyone is okay with it, right? We now start to apply this and start to talk about the mechanical properties. So we start to talk about the kinetic energy. I'm not going too fast, right? I'm 5.3 already. So we're going to talk, I'm writing this now. Kinetic energy and moment of inertia. Okay. I'm recording. OBS is still running. Okay. So the alpha is pointing towards us. Yeah, kind of. So if I'm if I draw the top-down view, yes. If I draw in the top-down view, is point. Well, if it's okay, so that it depends on the omega, right? So as we are saying, if it's rotating this way and if it's speeding up, then alpha is pointing towards us. But if it's rotating anti-clockwise, but the speed is decreasing, then the alpha is pointing down. Okay. Yeah, so is we start with the in the circle above. Yeah. So the one I was pointing to, right? Yeah, so we must start with the angular velocity direction first. Okay. Any other question? So okay, I think, yeah, so hopefully everything is so we're gonna start, this is a new section now. So if everyone is following the story so far, then I will start talking about this. Okay. Yes, so now we want to learn how to calculate the kinetic energy of a rotating body. And it has energy, definitely, and the reason is simple, right? We have calculated for translational motion, kinetic energy is half mv squared, right? And I have shown you by the work energy theorem and the calculations in the vector form is that the half mv squared, right, depends on the speed, right? It's a scalar, so the velocity is not so important anymore, you just need the speed. So anything with a speed will have kinetic energy. So anything moving carries kinetic energy. So same thing happens here, right? If you have a rigid body, I have multiple points going in circular motion. So when I have anything going in circular motion, there's a speed, and with this speed, it will have kinetic energy, right? So because it is rotational motion, we just categorize them under rotational kinetic energy. And when we talk about rotational kinetic energy, it turns out that it's not just the mass is important, and it's a combination of mass and the distance from the axis. So there was going to be a quantity that will come in when we talk about this, which is called the moment of inertia. So it is something like it will play the role of mass in kinetic energy, but it is a combination of the object's mass and the configuration that is important. Okay, so let's build up the concept step by step. What time is it now? Okay, so yeah, let's build up the concept step by step. Then it makes total sense. Okay, so yeah, because I'm saying this now because maybe the concept of moment of inertia is confusing for the students who are learning this for the first time. And you know, many times they just learn it as a formula, and then they memorize, and then they use, and then they. So if you memorize, right, it's not a good idea for physics, because when the question change a bit, what you memorize suddenly cannot be used anymore. So we need to start from the beginning. So let's start with the simplest case. Let's ignore rigid body first. Let's go back to a single particle. So let's talk about a single particle in circular motion of radius r. And then the speed is going at some speed v. Okay, so if it's going in a circular motion, right, so this one is no big deal. So the speed is v, the radius is r, the mass is m, then the kinetic energy is half mv squared, right? So this one is what we have learned since last time, but right now we learn a new formula, right? So we have learned that the speed is just the radius times the angular velocity. So I want to, instead of expressing this in v, I want to express in terms of omega. So I substitute the v inside. So my kinetic energy is now half m r squared omega squared. Okay, so the quantity that we want to define as moment of inertia is this mr squared. Okay, so I'm going to let I to be mr squared, so that my kinetic energy is just half I omega squared. So it looks very similar to the original kinetic energy formula, but the m has replaced by I, and this one is now, instead of v squared, it's just omega squared. Okay, so so this is the related to the angular velocity, so it's the velocity part, and this part depends on the object. Okay, so last time the mass, right, is what the object is. Right now is I. Okay, so yeah, so this is the moment of inertia for a single particle. So moment of inertia, so we call this the moment of inertia, right? So moment of inertia. Okay, so this is a new quantity, so let me put this of a single particle in circular motion of radius r. Moment of inertia depends on the radius, obviously, right? So if you're going in a bigger circle, you have a larger moment of inertia. Smaller circle, smaller moment of inertia. Okay, so this is what we have now. So the next thing is, well, single particle is settled. How about a collection of particles? So this will easily transition into rigid bodies later. So let's talk about a collection of particles. Okay, a collection of particles, but to make contact with rigid bodies later, we want them to have all having the same angular velocity and same axis of rotation. Same axis. Okay, so again I have an axis drawing top down, so as yeah, it's pointing, the axis is like sticking up towards us, and then I have different particles. Okay, so let's say I have object 1 having mass 1, and then this is going in radius 1, so it's traveling in a circular motion. Okay, and then I have another object here, so m2, and the radius is 2, so going in another circular motion, and then maybe I have a third one over here, so m3, the radius is 3, going in, everything going in a circular motion, so same angular velocity, right? So all going in a circle. And what is the total kinetic energy of the system? Okay, so the total kinetic energy of the system is the sum of all the kinetic energy. So object 1, object 2, object 3, plus everybody. So I got half m1 v1 square plus half m2 v2 square plus everybody. And again, I want to use v is equals to r omega. So for object 1, the v is the radius 1 and omega, right, square. And for object 2 is r2 square omega 2, and you add up all the other objects. Okay, so we know, because we want all the omegas to be the same, so everybody has the same omega, so I can factorize omega out of the equation. I can also factorize the half. So what I have here is half, right? It's only these terms are different, so mr square here, m2r2 square, m3r3 square. If there's more, you just mr square for all the others, but everybody have the same omega, I can factorize out. So this one will be the moment of inertia. Okay, so this is how we get half I omega squared. So this is the moment of inertia. Since it takes so long to write a long words, I'll just call this MOI, of collection of particles. Is given by the formula, right? Is let's say I have n particles, so I will sum up from 1 to n all the mr squares. So the ith object having its mass, and each object having its distance from the axis square. Okay, so this is the formula for the moment of inertia. So does anyone have any questions so far? If something is slowing down, the tangential acceleration will be opposite to tangential velocity. Correct, yes. So where is the omega pointing? It's still towards us, yes. So the omega is always the right hand rule. Omega is the omega vector. But don't worry about too much about omega vector yet. So most of the time at the moment we'll be dealing with the magnitude only. The reason is because omega is different from v vector. The v vector, right, you can easily imagine from the direction of motion, so we can visualize the v vector easily. But when we talk about omega vector, right, is the right hand rule. It's referring to the axis of rotation. So if it's rotating this way, then this is my omega vector. And then we ask a second question, is it speeding up? If it's speeding up, then the angular acceleration is here. But if it's slowing down, then the angular acceleration is pointing down. Okay, but the direction of rotation, if I change this, so if I'm now rotating the opposite direction, right, speeding up is still angular acceleration is pointing down. Okay, so the that's why vector for angular case is more troublesome, because you need to think many steps to get to the conclusion. But that's why I avoid it whenever possible. So the vector is follow no, I was saying first you think about omega, is it speeding, then the direction, and then speeding up or slowing down. That will tell you the direction of alpha. That's the many steps you need to consider. What vector are you talking about? Because alpha is a vector, omega is another vector, right? So okay, so you can meanwhile you can type questions, but now it's okay, so there's two cases. Just remember, it could be the same direction or different direction. So let's take since I seem to be going quite fast, so we can take a 10 minutes break and we come back in 10 minutes time, so 11:08. Okay, so let's take a 10 minutes break and I will stop the recording. Start recording. Yeah, so the black hole the black hole and me and my friends work on, usually they do not exist in real life. These are the theoretical black hole. The ones that exist in real life is always the Kerr black hole. It's just one solution. It's already solved long ago and nothing much to do there for theory lah. But for experiments and observation, that is another story, like the gravitational waves in recent years and things like that. Okay, so we have defined a new quantity which we call the, am I recording? Yes, which we call the moment of inertia. So new quantity, and as always, every time we encounter a new quantity, let's check what is their units. So let's look at the dimension. So basically the dimension is the dimension of this and the dimension of this. So essentially at the end of the day is everything has a unit of mass times the distance squared. So the unit for moment of inertia is very simple. It's just kg meter squared. There's no special name. It's just kg meter squared, right? Nothing special. So let us, before we go to rigid bodies, even point particle moment of inertia is quite important. So let us work out an example to see how this example will show us that the moment of inertia depends on the orientation and configuration of the system. Okay, so let's say we have a machine consists of 3 ball bearings linked by struts. So what is the system's moment of inertia if the axis is through A, when the axis passes through the center of the diagram, and then secondly, if it's perpendicular to the for part B is from this. So I have an object, right? An object can have different possible axes. So we try to work out how to calculate the moment of inertia of these different cases. So let me draw the picture of the object. Okay. So I have one ball A here, right, and then another ball here, and here another one. Okay. So the first question is that the axis is passing through here, right? So axis for part A, right? So what is the moment of inertia when my axis is passing through here? So that means if I draw a top-down view, right? So it's just rotating, right? So this thing is rotating around ball A. So how to calculate? Very simple. Just use the formula, right? The formula is just to sum up the m and r square. So for the first object A, the distance from axis is 0. So 0 distance from axis, r is 0, so the moment of inertia is 0. But for this part, for this ball, the mass is 0.1 kg and the distance is 0.50 meters. So so this is m, this is r square, and then the secondly, right, the mass is 0.20 kg. Make sure you use the correct distance. It must be over here, so 0.4 meter here. So the moment of inertia for part A is just this mass times this distance, right? And then this mass times that distance. Okay, so from here we can compute the answer, 0.057 kg meter square. So I guess one important thing to emphasize before I forget is that when we want to calculate the moment of inertia, right, this r is the perpendicular distance from the axis. Okay, so it must be the perpendicular distance, right? That will be clear when we start to do B. So if we are doing part B, right, the axis now, so the axis now, let me very quickly draw again, because now I have a different axis. So the axis now is here. Okay, then for this axis, so this mass has 0 distance from the axis, this mass 0 distance from the axis, so no moment of inertia. So the only moment of inertia is because of this mass, right? So for this mass, right, it is 0.3 kg. Okay, so it's mr square, right? So the object A distance and this thing square, so the mass is 0.3 kg. And which distance to use? You got two distances to choose from, right? Either this number or this value, and what we want is the perpendicular distance from the axis, right? So the axis that is straight towards here, which is 0.4, right? So 0.4. So do not use this number, use this one, so it's 0.4. Okay, so from here you calculate to be 0.048 kg meter square. Okay, and then for part C is just to calculate the kinetic energy. When we are in part C, the axis is rotating A, so the first case, right? So the first case, my moment of inertia was 0.057, right? And then the angular speed is omega is 4 radians per second, so just plug in the numbers. I think this is pretty straightforward, right? So my kinetic energy is half I omega square, so it's half 0.057 and then 4.0 square, so the kinetic energy is 0.46 joules. Okay, so for a rotating object, we are now able to calculate its rotational kinetic energy. Okay, so this is pretty straightforward, I guess, because everything here are still point particles. So why is what? Allow handwriting? Yes. Yeah, handwriting. Sure. You can write and then you scan the answer. MC is not perpendicular, we can use the R. In A, it's perpendicular. So it's a 3-dimensional picture. So I draw it this way, but it's a 3D picture. So it's like, so so my axis is here. Right, so my finger is perpendicular to this 0.4 line. This is part A rotation, right? So part A is rotating like this. Clear? Clear? Okay, yes, great. Yeah, so for when everything is point masses, everything is still pretty straightforward. So now we are going to this one, which is starting to be challenging for from what I see in previous students. So now we want to calculate the moment of inertia of rigid bodies now. Okay, so the kinetic energy and moment of inertia for rigid bodies. Okay, so when there are points, everything is fine. But what if I have a rigid body, right? So remember, what is a rigid body? A collection of every point on the body is rotating at the same axis and same omega. So I have some rigid body over here, right? Usually it's a circle, but yeah, so let me take some random example, right? So this rigid body consists of many infinitesimal points, so they all add up to create this body, right? So it has many points, and this is my axis of rotation. Okay, so let's say I'm rotating in this way. Okay, so how do I calculate the moment of inertia? So the moment of inertia is the sum of the moment of inertia of all these points. Okay, so so we can say that an extended body extended means it's not a point, right? It has a size, but an extended body is just a collection of many infinitesimal points. Okay, so we have many infinitesimal points. So that means, right, of mass dm. So if I want to use my original formula, right, so for the moment of inertia is that we want to sum up many points of mass mi, right? But if there's many infinitesimal points, if I summing up many small things, it is like a integration, right? So it becomes like this. Yeah, so this is like the Riemann sum. It becomes like a integration. We have already done this when calculating the center of mass, so the same concept works here again. And for the PHY students, I think you are taking calculus now. Around now should be still in the differentiation part, right? So don't worry about it. This is enough for us. But then later when you go to the different integration chapter, you will learn that this is the Riemann sum. I forgot to mention this for the center of mass, but this is like the Riemann sum. The math students already know this, having taken calculus the previous sem, right? So this is the Riemann sum. Okay, so the moment of inertia for a mass, right? So it's many points, right? So usually let's take one example. So one example here, this is having mass dm, and this particular dm has distance r from the center from the axis. Okay, so therefore the moment of inertia for rigid bodies is given by this formula. So instead of summation, I change this to integration. So what I have here is that I integrate r squared dm. Okay, so since I have time, I can go a bit slower, because this was the scary formula for center of mass, right? And it's very similar here. This is very similar to the center of mass formula, just that it's instead of x dm, there's a r squared dm, right? So so now I can go a bit slower to make sure everyone knows how to use this formula. So hopefully it won't be so scary after this. Okay, this is page 6. This is page 7. Okay, so this is the formula, right? And as always, this formula is in abstract form, which is why it looks scary for a student, because when we actually use it, right, we first need to convert this into something that is usable for integration. Now it's not very usable, right? It's just the variable is a mass variable, and then this is a distance variable, so it's like different things. So we need to convert everything to share the same variable and then perform the integration. So to begin, right, let us work out an example. But before I start, does anyone have any other question first? No? Okay, example 5.4.1, right? So in this example, we want to calculate the moment of inertia we are again a uniform rod, right? Just like we did for center of mass, but right now we want to calculate the moment inertia. Okay. Okay, so let's draw the rod. Okay, so in this case I have my x-axis, and then my axis is passing through the center, so this is my axis of rotation. So like it's basically just have a rod, right? So the axis of rotation is at the center, so it's like spinning like this, right? Spinning this way. Okay, so you can rotate this way. Then usually it's convenient to put my axis at the origin, so let me put this at my origin, and therefore this position is minus L over 2, this position is positive L over 2. Okay, so the length of the rod is L. Okay, so this is a rod of length L, total mass M. Okay, now let me start. Okay, and this time I'll do it more carefully and more clearly as best as I can this time for those who are still not so familiar with this. Yeah, so if you're familiar, maybe you'll be boring, but the scary part for student is usually dm, right? How do we handle this dm thing? So this dm is the infinitesimal mass. So this is a collection of many points, right? So let's look at one particular point. So let's look at one piece. Okay, so let's look at this piece. This piece has infinitesimal mass dm, and the length is very short, so we call this dx, right? It's just a small interval in the x-axis. How to derive which equation? You mean this one? This one is nothing to derive. This is just the definition of moment of inertia. Instead of summing up point particles, I'm integrating infinitesimal particles. Nothing much to derive there. It's just the definition of moment of inertia. So it's defined to be like this. Okay, so now, okay, yeah, moment inertia, yeah, it's defined. So it's just a definition. So we just start from there. Okay, so I'm going to use a slightly different approach from the center of mass last time by talking about this. So how do we talk about dm? So this is a one-dimensional rod. Okay, so one-dimensional rod, and the important quantity is the mass per unit length. So let's look at dm dx. Okay, so dm dx, and if this is a uniform rod, right? So for uniform rod, dm dx is going to be some quantity. If it's uniform, then this is going to be a constant. Okay, so that means what is the mass per length of this small piece? So the mass per length here is constant. That means it's independent of position. So the mass per length at this position is the same as the mass per length at this position and other positions as well. Okay, so dm dx is a constant, so lambda is a constant, right? So if this is a constant, I want to do something like this. So this is lambda dx. Okay, and then I know that my total mass is m. So to get my total mass, I just integrate dm, right? So let's see what happens if I integrate dm. So integrate dm on the right hand side, it just means integrate dx, but we have said that lambda is a constant because it's a uniform rod. So I got this, right? And once I have formulated into a position integration, I look at the limits of the position. So my rod is starting from minus L half to positive L half. So this shall be my limit of integration. So L half to L half. Okay, so if I integrate, on the right hand side, I got lambda x from L half to L half. And basically, I'll just get L because L over 2 minus negative L over 2. Okay, so the conclusion that I get from here is that yeah, so m is equals to lambda L. So this is the part I skip over quite fast when I talk about the center of mass, but it's the same thing. So right now is my chance to do it more slowly and more carefully. So I conclude I have derived the relation that lambda is equals to m over L. So which means that I got the result that this is equals to m over L. Okay, because I forgot who asked me last time, why is this equals to this, right? I remember someone asking me the question, something like that, right? But now I will, so now I have shown you, right? Why is it like this? Okay, so is anyone still not yet convinced by this relation, right? So that means I conclude that dm over dx is equals to m over L for uniform rod. Right, and therefore my dm is equals to m over L dx. Okay, let's see, does everyone follow the story so far? Everyone okay, huh? Okay, so if everyone's fine, now let's actually calculate the moment of inertia. So the moment of inertia for this object, right, is by using this formula, is defined to be r square dm. Okay, so remember, right, for moment of inertia we need to figure out the two pieces. So this dm, I already shown you how to get this, right? So we just need to substitute this in. But for this part, right, remember that r is the perpendicular distance. Of the piece dm from the axis. What do I mean? What do I put for r square here? It is the perpendicular distance, right? I have been telling you that this r must be the perpendicular distance. So if I take this as my dm, right, if my dm happens to be here, then what is my r? So my r is just this is my r, and it is the x coordinate. So this is why I put the origin. So it's going to be equals to the x coordinate of this object. Okay, follow so far? Right, so in this case, in this problem, r is just x. This is where you have to be careful, because sometimes it's not just x you put it in straight away, right? Sometimes it's x minus d for certain situations, depends on where is your axis. Okay, so if you draw a piece, then r is the distance of that piece from the axis, right? If you draw this piece, then it's this distance, right? You just take one representative example of a piece, and this is my r. Okay, then after that you sum up all the pieces, so you integrate. So this is where the integration comes in, right? So what I have here now is that if I substitute in all the pieces, I got x squared, then the dm is just m over L dx. So m over L, we have shown that it is a constant, so let me take it out. So all I need to do is just to integrate x squared with respect to dx. Okay, so once I have formulated into an x integral with respect to dx, now I know what to do. Now I know where to put in the limits, right? So I need to sum up all the pieces from left to right. So my first piece is here at L over 2, and then my last piece is positive L over 2. So that fixes my limits. So it's from minus L over 2 to positive L over 2. Clear so far? Okay, now let's see, right? So let's try to integrate. So m over L, if I integrate this, I just get 1/3 x3 from L half to L half. So this 3 is another constant, and then basically I got L over 2 square minus the lower limit L over 2 square. Okay, hang on, integrate. I make a mistake for integration. This is integrating x3, right? So integrating x3. Yeah, so it's over here. So m over 3l, and then l over 2 to the power 3 is not square, L over 2 to the power 3. So that was my mistake. Okay, so simplify this. I got m over 3l. So this will become l cubed over 8, right? 2 to the power 3 is 8. minus 1 power 3 is minus 1. You will become positive together with this, so it's L3 over 8, right? So if I add up the two numbers together, I got L3 over 4. So at the end of the day, 3 times 4 is 12, so it's 1 over 12. This will cancel with one factor, is ml squared. So my moment of inertia of a rod passing through its center is 1 over 12 ml squared. Do you follow so far, everybody? Any question? Nice story. Okay, everyone okay? Huh? Which story are you talking about? Okay, so yeah, let me slow down a bit for everyone to digest, because I went a bit too fast for the center of mass last time. And this part is the tricky part for most students. Now, after we are done with this, right, I want to show you another situation. Oh yeah, I did. Yeah. Okay, great. So everyone is following the story. That's good. Okay. That reminds me, speaking of study tips or advice, right? This is how I think of when learning physics. It is a story. It has chapters, right? So you need to, and just like any other story, right? If you just jump in and watch the ending, you don't understand anything, right? So yeah, if you just suddenly jump in to watch Avengers Endgame, you don't have no idea who everybody is, right? You need to watch at least some of the previous movie first. And why I bring this up is because I see some student, right? What they do is, again, this is the issue of last minute studying. You know, when you want to study for exam, they think they want to save time. They don't want to waste time going through the lecture notes again. So what they think is, okay, they just jump straight to do the question. And then a lot of students do that, right? And I can get this sense by a lot of people asking the question. They seem to jump the question without reading the lecture note. It's not a good idea. Maybe it works for high school, because the high school exams, they are quite standard, you know, solutions and methods, and students can memorize the question and the answers. But for like university type of physics, right, cannot, because a lot of it depends on the concept. So it's worth the time to go through the lecture notes, and then you understand the story first, and then when you see the problem, you know what to do. Because if you just memorize, just jump in to do the question, right, you jump the question and then you want to find the solution, you know how to do exactly that one question. But when the exam comes, they just modify the question, then student cannot do already. So that is what a lot of students struggle with all the time, right? So yeah, so that is the thing. But any question about moment of inertia? No? So let me add one more situation. Okay, I want to emphasize this because the moment of inertia depends on the axis. Okay, so the same object can have different moment of inertia if I have an axis on a different place. So let me add on to the example. Okay, so this is not in the lecture notes, but I can show you this. Okay, so let me now say that my axis is now here. What is the moment of inertia for this case? So still rod of length L, uniform rod. Total mass M. Okay, so what is the moment of inertia when my axis is here? So just now my rod is spinning here, but now I put my axis here, so my axis of rotation is here, so now it's spinning like this, rotating like this. Okay, so we do the same thing as before, right? Our moment of inertia formula has r squared dm. We need to identify r squared, we need to identify dm. So let's look at dm. So there are many pieces. Let's choose one example of a dm. So one dm is over here, so the mass is dm, the length is dx if I use this as my x-axis. So if I put this as my origin, this should be x equals to 0, this should be x equals to L. Okay, so what is the distance of a point from the x-axis? The distance of the point from the x-axis is how far away, right? So I want the perpendicular distance, and the distance is just my x-coordinate. Okay, it's just my x-coordinate. And because this is a uniform rod, total length L, total mass dm, therefore I have dm dx is equals to total m over total L, right? So dm is just m over L dx. Now let's try to find the moment of inertia. So the moment of inertia is, the formula is r square dm. So this is why we need to identify the two pieces, right? So we have found r square is just my x coordinate, and the dm is just this thing. So it's just m over L dx. So we got the same thing as we did last time, but we expect a different answer because we look at the limits of integration, right? So I need to sum up all the pieces, right? So this is just one piece, but every other piece have different distances. My first piece is position 0. My last piece is at L. Okay. So yeah. Now what happens? So I'm integrating this from 0 to L. So same thing. So it's the same integral but different limits. So I got 1/3 x to the power 3 from 0 to L. So the lower limit is now just 0. So I got L 1 over 3, L 3, and then the second term is just 0. So my answer is just 1 over 3 ml square. Okay, so it's different from the previous answer. Previously was 1 over 12 when my axis was at the center, right? But now it's 1 over 3 ml square. Okay, so still a nice story, I hope. If you understand everything I'm talking about now, right, then you should have no more problem calculating moment of inertia. Okay, maybe the question will be a bit tricky, right? The shape will be tricky, but the method at the end of the day is the same. So there's not much thing to worry about. So I guess I have about 10 minutes left. So let me add another thing. So the calculation that we did so far, right? So if everyone is following the story, this is the next part of the story. So the calculation that we did, we are assuming all straight objects, okay? But eventually, right, sooner or later, we will encounter circular objects. So I want to add in another example. Okay, let us try to calculate the moment of inertia of a uniform thin ring. Okay, or like something ring is a hula hoop, so it has a moment of inertia because you can make it rotate. So how do we calculate the moment of inertia for that case? Okay, so uniform thin ring, then same thing, total mass m, radius capital R. Okay, so I have a uniform thin ring. Okay, so the radius is R, and then let's say my axis is here. So let's take this to be my axis. Okay, so it's a thin ring, right? So so it's a uniform thin ring, and let's look at one piece. So it consists of many pieces forming the circle, and let's look at one particular piece. Okay, so this one particular piece is having a mass dm, and then the length here is well, now let's call it ds because it's more like a small arc length of a circle, right? So this is a uniform thin ring. So that means the mass per length of this piece, right? What is the mass per length here? So the mass per length is something, and because if it's uniform, so if uniform means lambda constant, if it's not uniform, then at different positions I have different densities, mass per length. Okay, so now I want to try to express lambda in terms of the total mass. Okay, so what I got is, well, let me move this aside. I got lambda ds, and then I try to integrate this function. So what is ds? So ds is arc length of a circle, right? So if I draw an arc length of a circle, okay, so let's say my center of the circle, so my circle is, center of my circle is here, right? So if this is my ds, okay, so I can convert this in terms of theta. So ds is equals to r d theta. Do you agree? Right? So arc length is just this times this in, if I'm talking about radians. So ds is equals to r d theta. So I'm going to replace this. So that means I'm going to say that ds is equals to r d theta. Therefore, my dm is equals to lambda radius times d theta. Okay, but my radius is capital R, so I should be calling this big R. Okay, so this is a constant, this is a constant. So if I want to get the total mass is just the integral of dm, which is the same as integrating lambda r d theta, and these are constants, so I can take it out of the integral. So I got lambda r integral d theta. Okay, then we look at the limits of integration. So my basically my first piece is theta equals to 0. After I go one round, one full angle is 2 pi. Okay, and you guys are saying that this is tau. Okay, so but I guess I'm more used to calling this 2 pi. So lambda r, so basically I got lambda times 2 pi r, right? So it's just the same as the circumference of this circle. In other words, my lambda is m over 2 pi r. Okay, and I conclude that dm s is equals to m over 2 pi r. Okay, so we are going to, because we need this later, we need this for my dm substitution. So dm is equals to 2 pi r ds, and we have also said that ds is equals to r d theta, so that we are going to use this later. So dm is m over 2 pi r, and then we notice that this is r d theta. We can cancel one factor here, so dm is m over 2 pi d theta. Okay, so I have my dm now. Okay, so what is my moment of inertia? My moment of inertia is r square dm. So we need to, as again, right, see, the step is always the same. I need to know what is this thing, I need to know what is this. This one found already, so it's this piece. Put it in here. How about this? So this is the distance from the axis. So every point, all of these points are always having the distance capital R from the axis, right? So every point is the same distance. So therefore, it's easy. It's just substituting in. I get r square and then m over 2 pi d theta. Okay, so I can simplify by taking out the constants. So I got m is a constant, r square is a constant, 2 pi is another constant, and then I'm integrating, my variable is integrating theta. So my theta goes from 0 degrees, one full circle, so 0 to 2 pi. Alright, so it's just mr squared over 2 pi and then times 2 pi. So cancelling this, so the moment of inertia of a ring is just mr squared. Okay, so this is the moment of inertia of this ring. Okay, any questions so far? So everyone okay? Let's see what we have next. Okay, just 2 more minutes. There's many things to show you, but now it's too late to start a new thing now. So yeah, I was expecting to be going very slow in this chapter, but somehow
I went through very fast. I don't know why. I hope no one is lost. So what we have been calculating, right, is actually ultimately what I hope to do is try to build up this list. So now last time, so usually, this one is, we never expect students to memorize this, but at least should know how to derive this, because sometimes the question just asks you, right, how to calculate the moment inertia. You need to show how you get this answer. So what we have been doing, right, we have already calculated the moment inertia of a rod, 1/12. We got this. We also got this case, right? And for the ring, it's not shown in the picture, but there's this thin wall cylinder. It's just a stack of rings, so it just is the similar formula as well. Okay, so it's this mr squared, and I will maybe in the next class I will show you how to relate this to this later on. And also later I want to show how to get this actually for two-dimensional object. Everything we have been calculating so far, is talking about one-dimensional object, right? We should at least know how to calculate two-dimensional object. Now, the formula to get two-dimensional object, if you calculate from scratch, right, is actually using multiple integrals, using the stuff that you learn in calculus 2. But in the next class, I will show you how to calculate in a way that you don't need calculus 2, right? Just normal integral, but we can still calculate the moment of inertia for two-dimensional objects. Okay? Okay. Any question? No? 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 So if not, that should be all for today lah. Yeah, let me stop the recording.